Recording. Okay. Here we are, lecture 14, continuity and compactness. So, we studied compactness a while ago. I guess right before continuity. And we've just been studying continuity. And now we're going to relate the two. And basically, there's one theorem that relates them. It's incredibly useful. That's going to be our main result today. It's not so difficult to prove. In fact, Cal leaves this proof as an exercise, but I think it's a little bit too important to leave it as an exercise. So we're going to prove it, and then we're going to do two consequences of it today. There's other important consequences for uniform continuity, but we're either going to see those Friday or Monday. I haven't decided yet. Okay, so here is the result. It's the big result of today. Let's call it a theorem. Because it is pretty important. Okay. So we're going to have two metric spaces. And we're going to have a continuous function between them. And we're going to have a compact set in the domain. And then the conclusion is that the image of that compact set is compact. Okay, we could easily state this just by saying X is a compact metric space instead. Then we could just say that the range of F is compact. Okay, so we could save a few words there, but this is the same thing. So we've just got a compact set in the domain. It's mapped to a compact set. Okay. Any questions about what the theorem says? Okay. So now let's prove it. The key is just not to get yourself. It's kind of a straightforward proof, except that there's a few moving pieces, so we have to not get ourselves confused. Okay, F is mapping X to Y. K is going to be some compact set in the domain. So there's some F of K over here in the range. And then, we want to prove that F of K is compact. So we're going to take an open cover of it, whatever your favorite open cover of it is. And we're going to argue that that open cover has a finite subcover. So let's get started. We're going to take an open cover of f of k. Usually we let script u be our open cover. But when I was writing this proof, I thought it might be nicer to pick script w, because this is all happening kind of in the range, not in the domain. So let script w be an open cover of f of k. Okay. Now, every point of k has its image sitting over there in f of k. So now if we look at the preimages of the sets in W, we're going to get an open cover of k. Okay. So what would that be? The family, it would be the preimage of every set in W is an open cover of k. Okay, and that's just because you think, I'll write it over here on the side. If x is a member of k, then it has some f of x in f of k. And that f of x is in W for some open set in our cover. So our original point x is in the inverse image of that. We're good so far? Yes.
Don't we only get an open cover because of the continuity?
Oh, I'm sorry. I meant to just say it's a cover right here. And now I'm going to say that because of continuity, it's an open cover. So yes, to your point. This family is an open cover because F is continuous. Okay. Why does that work? Well, the preimage of an open set is open. Remember, that's our alternative definition of continuity. Okay, so we already knew we had a cover, and now we observe that every set in our cover is open, and that makes it an open cover. Okay, good so far? Now, K is compact, and we've just made an open cover of it, so we can take a finite subcover. So since K is compact, this open cover has a finite subcover. Okay, now we're going to do kind of our normal thing. We've done this several times when we're doing compactness proofs. we want to observe that if we've got finitely many of these things, remember I'm talking about this family, okay, then what we've really got is we've got a finite subcollection of W, okay, and then we're looking at the inverse images of those. Okay, so we're going to do this kind of relabeling. Well, I wouldn't even call it relabeling, but let me just write what we're going to do. Thus, there is some finite subfamily. This isn't, well, anyway. F in W, so that the preimages of those are the finite subcover of K. Okay. And really, what I want to write here is that they are a cover of K. So that would mean that K is in their union, being the union of all sets W in this finite family, F, of the preimage of the set. Okay, so what did we do? We took our open cover of our image, we translated it back to an open cover of K. We got our finite subcover. That's this F. Right. Now, but what we really want is a finite subcover of the image. So what do we want? We want some collection of sets. Some collection of some finite subcover of W that covers the image. Now, let's see, I wrote this, did I write this a little bit backwards? Maybe this would be better if I wrote it backwards, but let me try this. Observe the following slightly unmotivated observation. If you looked well, sorry, I'm just trying to motivate this. Yeah, okay, so clearly we're trying to find a finite subcover of W. Clearly this is the one we're going to try and show is our finite subcover. It's F, okay? So now how are we going to show that? Well, I mean, it's a finite set. They're all open by definition. So what we need to show is that they cover K. Okay. Well, what do they cover? These cover if I union up all those W's in F, I contain the union of the images of the pre-images of everything in W. Pick a particular W. W is on the other side. Oops. So here's the thing, W might not, let me do it this way. That's the image f of k. A particular W would be an open set over there in Y. That's Y. Okay. Now we look at its pre-image. That's the things that map to it. That's going to be a set over here in X. Okay. Okay. And then we follow that pre-image as we apply F. Now here's the thing. This is a proper subset. Oh, no, sorry. I don't mean to claim it's proper. We can't rule out the possibility that it's proper. Right? We can't write equality there because we may well have lost points. Okay? Because we cannot claim that every point that's in this set W is actually an image of F. Okay, some of the points in W might just not be mapped to by F. Because some of the points at W can lie outside F of K. Okay? But what we can do is we can claim, if you look at the pre-image and then you apply F, you will end up inside W. Okay, this is me spending a long time on something that's actually kind of trivial. The fact that you take something over there in the codomain, some set in the codomain, you look at the pre-images, you apply F, you'll end up inside that set. Okay. Now, here's the thing. That is a union of images of F. Okay, so you think you've got a union of F applied to sets, images of sets under F. That is the same thing as the image of the union. Okay. Now, that's just true on a kind of on a set level. I mean, that's a true function about sets and functions. Sorry, that's a true statement about sets and functions. Okay, now what do we know? We know that. We know that these pre-images, it's right here, those pre-images cover K. So K is a subset of that. So now I'm looking at images of a set. Well, I contain the images of any subset. That's it. That's what we wanted to show. So F is a finite subcover of W. And that proves that the images, the set of images, f of k, is compact. Okay, so we just remember this theorem is saying the continuous image of a compact set is compact. Are there any questions about any of those? Benjamin says that we could make a proof of this theorem using epsilon delta continuity and sequential compactness. Well, I'm sure that's true. No, I'm sure that's true, that you can do that proof. I don't know if it's that much easier. So we take a sequence in the images. Let's entertain this thought for a second. We take a sequence, it would be a sequence of the form in f of k, right? And then we would argue yeah. Yeah, I think you have a good point, Benjamin. I think this might be a lot easier if we use sequential compactness. So we'd have to use sequential compactness, what we know about continuity and limits, and that would work. Yep. I think the reason that this is the proof, so the proof I just gave is the proof you always see. And I think the reason for that is because this again, this holds more generally. This proof holds for topological spaces. But, you know, again, we don't care about topological spaces in this course. So the sequential compactness proof would be fine. Any other questions? Okay, so two consequences. The first one is a result we remember from last semester. The extreme value theorem is now basically immediate from everything we've built up. Okay. So, would anyone like to volunteer to remind us of what the extreme value theorem said last semester? Did we call it the extreme value theorem? I think we did.
Was it that on a bounded set there's a maximum and a minimum?
Yeah, so a continuous function on a closed and bounded interval achieves its maximum and minimum values. Yeah. And really, you only need to say one of the maximum or minimum, because you could just look at the negative of that function and, you know. Okay, so what this used to say last semester was, just to repeat, and I'll simplify it, I'll just do the maximum. A continuous function on a closed and bounded interval attains its maximum. Okay? Now, how are we going to generalize it this semester? Well, if we want the conclusion to be, you know, attains its maximum value, then our function is going to have to map into the reals. Because only in the reals do we have a notion of a maximum value or a minimum value, right? I mean, in an arbitrary metric space, we just don't have notions of order like that. Okay, so our codomain is going to have to be the reals. Okay, but we can generalize our domain. So we'll want our domain to be, you know, last semester our domain was also the reals, but this semester our domain can be any metric space. Okay, and instead of a closed and bounded interval, let's just take a compact set. So that is our version. And I'm going to state this in the version where we actually restrict to the compact set. So I'm going to state it as a compact metric space as our domain. Slight hitch. We have to assume that, or we have to insist that our space be non-empty. Okay. So our domain is a non-empty compact metric space. F is a continuous function from there to the reals. If in this course we ever forget to say what our metric is on the reals, we always mean it's the standard metric. Then F attains its maximum. What do we mean by that? We mean there is a point, let's call it x sub max in X, such that f x sub max is greater than or equal to all the other points. Okay, we good? Any questions?
I have a question.
Yeah.
About how, a statement of saying maximum. Would it also be correct and maybe useful to say that instead of saying there's one that's greater than all the others, state it as there's an element in X whose image is the supremum of the image of the whole set is equal to the supremum of all of them. I guess that's kind of the same thing.
Yep.
Okay.
Um,
I guess if you use the supremum, you'd end up decomposing it to this anyway.
right. So, there are some people who use supremum all the time. And then there are some people like me who, uh, if something is a maximum, I like to just call it a maximum. Whereas there are other people who, they like to use the word supremum for any supremum, even if it happens to be a maximum. Does that make sense?
Yeah, that makes sense.
Okay. Benjamin asks, why do we have to worry about the whole metric space? Why not just a compact subset? So this is equivalent to doing a compact subset. If if X were not compact, or sorry, I mean, that's not the point. If we were only concerned about some subset that was compact, okay, remember we proved compactness is intrinsic. So we can just restrict to that metric space. We can restrict to K together with, we restrict our metric to K cross K. Right, and then that would be a compact metric space. Is that okay? So we haven't lost any generality. All we've done is save a variable. Okay. Frequently, you also see our first theorem done in the same way, where you wouldn't have this compact set. You would actually just say that X itself is compact. And it's the same thing. It's the same thing. Okay? Now, if you keep everything in mind, everything that we've learned basically the entire semester, then it's a very quick proof. Okay. The image, I guess this is the range. The range of F is compact. That's our previous result. Okay? Now, we're not using anything special about the reals here. Any compact set in any metric space is closed and bounded. So this range is closed and bounded. And now also we assumed X was non-empty, so F of X is non-empty. Okay. Now, finally, we need to appeal to the fact that we're in the reals. Now we need to say non-empty, closed, and bounded. Closed and bounded subsets of the reals contain their maximums. Okay. So there's some value in the range which is greater than or equal to all the other values in the range. Okay, now, that's not quite what we want. What we've written there is really just an upper bound on the range. Where do we get that this value is actually attained?
The preimage of M is in X.
Well, by definition, it's in f of x, so it has to be.
Mm-hmm. Perfect. Yeah, since we took it in the range, it is the image of a point. So there is some point, and we'll call it x max. And now f of x max, I guess I might as well just say the full thing. Okay. I can't quite remember how we proved this last semester, but I know it involved some supremums and stuff. This proof is pretty painless, you know, assuming all the knowledge we've built up. Although, you know, there's a bunch of proofs involving supremums hidden in this proof. Okay. Okay, but really, I mean, really that proof, we wrote a lot of sentences there, but it can really be condensed down into one sentence, which is, if you have a compact domain and a continuous function, then your range is compact. And since you're in the reals and you're compact, you have a maximum. That's it. Okay? If our codomain weren't the reals, but it were like the plane, okay? Well, you could still, you'd still have a compact range, okay? So you could still get a lot of mileage out of that, okay? You just couldn't talk about a quote-unquote maximum because, you know, we don't have the notion of a maximum on the plane. But you could still get a lot of mileage out of just having a compact range. Okay, so this theorem is one way to see that our first theorem is very useful. I'm going to give you another application of our first theorem. This is sort of neat. We saw like the shadow, the dimmest shadow of this result last semester. Let's again take a compact metric space as our domain. And our range could be anything this time. So compact domain, any range, F, it's going to be continuous, but now I'm going to add that it has to be a bijection too. Okay, and you know, if you have a bijection, you have, now by F inverse, we don't mean pre-images. We mean literal inverse, okay? Because if you're bijection, you have a literal inverse function. This inverse is also continuous. Does anyone remember us using this theorem last semester? So this theorem is how we established that, like, the natural log is a continuous function. Okay? Because we said the exponential function is a bijection. And then we actually, if you go back, we actually restricted it to a closed and bounded interval. And we said on this closed and bounded interval, natural log is continuous. Okay, using a much weaker version of this theorem. Okay.
I have a question about this statement.
Yeah, go ahead.
So if F was not a bijection, but instead just injective, could you make the inverse from
Yeah.
the range of x to, or from y to the range of x instead?
Yeah. Yeah, so, right. All you really need is injectivity, and then you can fix the surjectivity by restricting the codomain. Yep. Okay, so, right, so we don't really need that, but we're going to state it that way just to make the proof go nicer, and everybody knows we can, not only can you restrict, right, so you might want to restrict the domain, you might want to restrict the codomain to be just the image of the function. You know, you might also want to restrict the domain to be a place where you're injective. Okay, and then you really get the result that, you know, if there's any place where you're injective, then your inverse is also continuous. Okay, so it's a really powerful result.
I have a question about those restrictions.
Yeah.
Are those restrictions ever gonna ruin our compactness?
No, we're always allowed to restrict, and compactness remains the same. So that's the intrinsicness of compactness. Oh, and restricting on the codomain side doesn't matter because we have no demands on the codomain here. Right? We just said that it's any metric space. Okay? I'm going to have to rush through this proof a little bit because we've only got 3 minutes. But we want to prove that F inverse is continuous. Okay? So we want to take an open set in the domain that's in X, and we want to show, I'll write it down. We want to show that that thing is open in the codomain. Okay? Now, technically speaking, the inverse in the middle there is a literal inverse, and the way we've defined things, that one is just a set of preimages. Okay? But since we're one-to-one, so since we're injective, the preimages of the inverse images of U are the images of U. So what we really are proving just as a commentary in here, what we're really proving is that under our hypotheses, we're mapping open sets to open sets. Okay. Remember, that's not the definition of continuity. Instead, this is what you're tempted to think the definition of continuity might be. Okay? But this is sort of the opposite of the definition of continuity. There's a term for these functions. They're called open maps. We don't study them in this course. And you can be an open map without being continuous, and you can be continuous without being an open map. But when your domain is compact and you're injective and surjective, then what we're proving here is that if you're continuous, you are an open map. Okay, but you don't need any of that for the proof. Now a couple more lines. I realize we're out of time, but we're so close. All we have to do is play with open, closed, and compact, and we get it. So since U is open, and this proof will be in the notes, so don't feel strained to copy it all down right now. Since U is open, its complement is closed. In fact, we can do a little bit better. This is a closed subset of a compact set. The compact set is X itself. Okay? A closed subset of a compact set is compact. F, since it's continuous, it maps compact sets to compact sets. Every compact set is closed. Now, the one thing we haven't used is that F is onto. F maps to everything. So since F is onto, the images of the things not in U are the things not in the image of U. Okay, and now that's a closed set, we just said. That means its complement is open. And there we go. Okay. Sorry we had to rush there at the end, but like I said, we just play with open, closed, compact. The sort of interesting thing is that we take a closed set and then we have to kind of it's closed, but we have to wrap it up into compactness in order to get our function to preserve the closedness. Okay.